Hello and welcome to Mrs. Jones Chemistry Videos. We're going to try this out this time, and something to keep in mind as you are watching these videos is that I'm going to go pretty quickly because I got to get it in my 15 minutes. So if you need to at any point pause the video and kind of think about what I said or rewind it, feel free to do that. But we're going to start out talking today about LeChat principle, and this basically comes down to stress, and it's stress on a chemical equilibrium system. So let's start out by looking at a real-world problem that LeChat principle is going to relate to. Ammonia, or NH3, is used to make fertilizers and explosives. It is used around our country every day. And maybe you've heard about this before, a not so pleasant experience with ammonia where Timothy McVeigh blew up the Oklahoma City building. You were probably really little, if not you weren't maybe even born at that point, but it can be used for bad things too. But this process is known as the Haber process of making ammonia. And it's where you take nitrogen gas and hydrogen gas, put them together, and you make NH3 or ammonia gas. And here's Mr. Fritz Haber, and yes, he knows, he looks like Dr. Evil. But notice how this equilibrium favors the reactants. It is very heavily going back towards N2 and H2 gas, which is not what we want. We want to use this product. We have plenty of this stuff. So we need a way that we can get more NH3 from this type of reaction. We wanted this to be a high KEQ, not a low KEQ. So this is where this dude LeChat comes in. He figured out that you could do stuff to equilibriums to force it one way or the other. So to force it towards the products or to force it towards the reactants. He called this shifting the equilibrium. And here's Chef to tell you more about it. Not that chef, but this chef. Essentially, LeChat principle says if a stress is applied to a system at equilibrium, the system will shift left or right to minimize the stress. So it will shift towards the products or shift towards the reactants. So it will make more products or make more reactants to try and minimize what's happening to it. You might be thinking to yourself, what? Well, pretty much all that's happening is whatever you do to the equilibrium, it will try to undo it. So you might be thinking to yourself, stress on an equilibrium, stress on a chemical system, what kind of stresses are there? Well, there's three main types of stress that you can do on an equilibrium system. You can add or remove reactants or products. So put some in, take some out, and that's going to affect what happens in that reaction. You can increase or decrease the temperature. You guys have done this a lot in your labs, where you increase the temperature to try and get it to react faster, or decrease the temperature sometimes to get it to react faster. Sometimes this is like a catalyst, but sometimes this is just shifting an equilibrium. You can also increase or decrease the pressure, and you do this by changing the volume of the gases that you're using. So let's look at this stress number one, adding or removing the reactants or products. So if we look at our reaction that our Haber process, our N2 gas plus our H2 gas to make our ammonia, we want more ammonia. And so we're sitting here thinking, how do we make more ammonia? So we're essentially asking, how do we shift this equilibrium to the right? So if we look at our stress number one, which is adding reactants or removing products, if we add more N2 or H2, add more reactants, that means we're adding more of these. If you think of this like a balance, so I'm going to draw two little scales here. And on one side are our reactants. On the other side are our products, like the scales of justice. If you think about an equilibrium, you want all of those to be equal. But if you add more N2 or H2, this is going to get a lot heavier. It's going to go down. This is going to get a lot lighter. It's going to go up. In order for that to rewrite itself, more product is going to have to be made because this needs to go back down. So the equilibrium is going to shift to the right because you added a bunch of N2 or H2, and the only way for that product side to go back down is to get rid of the reactant and make the product. On the other side of things, Another way to make more NH3 would be to remove some NH3. So if we think about our scales again, starting out at equilibrium, we have our reactants, we have our products. If we remove NH3, this goes up, this goes down, and in order to rewrite itself, all of this has to shift to the right. These reactants have to start making products in order to get our product side of the scales to go back down. So think about it as it always starts at equilibrium, and anything you do to it, it has to fix itself. So the equilibrium will shift to the right in order to make more NH3 in this case. So in general, if you add reactants or you remove products, the equilibrium will shift to the right. It's trying to convert all those reactants into products. If you do the opposite, if you add products or if you remove the reactants, the equilibrium will shift to the left, to the left, to the left, to the right, to the right. I hope you're singing that song in your head because I am. Anyways, it's going to convert your products into reactants. It's always trying to minimize or correct the stress that you put on it. So let's go to stress number 2, increasing or decreasing the temperature. Yep, there's another one. In order to know how this equilibrium is going to change, you have to know if the reaction is exothermic or endothermic. So we worked with this a little bit in thermo, so you should know how to do this, but most of the time I will tell you. Remember that exothermic is a negative delta H, heat is given off or being produced, and endothermic is a positive delta H, heat is being absorbed or used. So a helpful tip here, something that will help you figure this one out, is to write the word heat into the equation and treat temperature changes as if you were adding or removing a reactant or product. Okay, so you can either write the word heat or you could also write the amount of heat if you know what that is. But for example, if it were exothermic, that means heat is giving out. That means heat is a product. So in our equilibrium here, we would write heat on the product side. If it were endothermic, we would write heat as a reactant. We're putting it into the reaction so that something else will come out. So in this reaction, methane plus oxygen yields CO2 plus water. It's a combustion reaction, so heat is coming out of that combustion. What direction would the equilibrium shift if the temperature of the system were decreased? So think about this again. Think about your scales. We have reactants and products, and this time heat is a product. So essentially we are forcing this up. We're taking away some of our product. So our reactants would go down. So in order for this to recorrect itself, we need more product. And the way you get more product is more reaction. So it will shift to the right, to the right, to the right. How about this one, an endothermic reaction? What direction will the equilibrium shift if the temperature of this system is increased? Okay, so in this one, again, if we think about our scales, reactants, products, we are increasing something on the reactant side. So it's like the reactants are getting heavier. Products are getting lighter. In order to redo this and to get it back at equilibrium, it's going to have to shift to the right to make our product side heavier. So to the right. So, summary of stress 2, increasing or decreasing the temperature. Hopefully you are not at this point, but if you are, it's okay, we'll do a little bit of review in class. But to review stress 2, if temperature increases, the equilibrium shifts away from that heat. If temperature decreases, the equilibrium is shifting towards the heat. So, stress 3, last one, increasing or decreasing the pressure. Now think back, pop quiz real quick, think back to when we went over gas laws. Which cylinder here has the highest pressure? Notice that they all have the same amount of gas particles, but the volumes are different. So the one with the smallest volume is going to have the highest pressure. That's because as volume decreases, you get more collisions, and so pressure's increasing. Pop quiz on this one. How would adding more gas particles affect the pressure in the cylinders? Again, it's all starting out with the same amount, but they're at different volumes. What's going to happen when we add more? Well, obviously it would increase the pressure because we're increasing the collisions with the sides of the container. So, in summary of that, if volume decreases, pressure decreases. If volume increases, pressure decreases. More moles of gas equal more pressure, and fewer moles of gas equal less pressure. So let's take that, what we know, and look at our rule 3, how pressure is going to help the equilibrium shift here. Which direction will the equilibrium shift if the pressure is increased on this system? Well, we have to look at the number of moles of gas. Here we have 4 moles of gas, and here we have 2 moles of gas. So if we're increasing the pressure, it's going to try and get rid of that increase, and it's going to want to decrease it. So our equilibrium is going to shift to the right because it can decrease the pressure that way. If we have 4 moles of gas and 2 moles of gas, remember that more moles of gas creates more pressure. So by shifting this direction, we decrease by half our pressure because we no longer have as much gas. How about this one? Which direction will the equilibrium shift if the pressure is increased on this one? Well, we have 1 mole of gas, and on this side we have 1 mole of gas. This is a solid, so it doesn't create pressure. So this one's a trick question. The number of moles of gas on each side of this one are the same. So it's important to note that the equilibrium is not going to shift here. There's nothing that's going to equalize it by reacting. So, in summary of stress number 3, increasing or decreasing the pressure. If the pressure increases, the equilibrium will shift to the side with the fewer moles of gas. And if the pressure decreases, the equilibrium is shifting to the side with more moles of gas. Pressure and volume change will only affect systems with unequal numbers of moles of gases. Remember, it's trying to decrease that stress. And if it doesn't do anything to decrease that stress because it's equal on both sides, it's not going to do it at all in general. So this is the end of these notes. If you have any questions right now, feel free to email me, shoot me a message on Schoology. Otherwise, we will talk about this in class, and I will see you guys then. Peace out.